external potential. And for example, when we apply static bias on graphene, this is the static calculation of Berry curves, and this is the whole velocity calculation obtained by the real-time evolution of the TD-DFT. So the whole velocity of the electron at the k value and the whole velocity of the electron at the k prime value is very well produced. And we applied this concept to the so-called the topological insulator quantum spin hole system by calculating first by calculating the time dependent Cohen-Sham spinor state, and by calculating the charge hole velocity operator, so the charge current and spin current. By calculating these two concepts, we can arrive we can calculate the topological state of the quantum spin hole system. For example, this is the bithmethane, the very well-known quantum spin hole, two-dimensional quantum spin hole system. By using the time evolution technique, we obtained the quantized spin hole conductivity, one quantum of spin hole conductivity, but the charge hole conductivity in this system is 0 because of the time reversal symmetry. And we can analyze each band contribution to this quantized spin hole conductivity. So this system, we show that not the valence band, the highest valence band, but the second valence band is mostly contributed to the single quantum of spin hole conductivity. We applied the same time evolution technique to the Spin-Phonon dynamics, and in this case we assume that some light, for example, the IR excitation, some light is applied and some phonon is generated, phonon is pumped, then there is some change in the scalar potential. Then our motivation is that let's calculate the time evolving the electronic state, and let's derive the spin dynamics by calculating the expectation value. So the one example of our study is that the single layer molybdenum disulfide MOS2, and this is just a simple insulator, the topologically trivial and time reversal symmetric insulator. The time reversal symmetry in solid state means that all electrons are paired by all electrons constitute the Kreimas pair. Kreimas pair means that the electrons at K, the spin down electron at K should have the same energy, the same band energy as the spin up electron at the minus K. So this spin momentum pair is a consequence of a time reversal symmetry. It is so-called Kreimas pair, Kreimas pairing. And around 2013 and 2014, many groups try to kind of breaking the time reversal symmetry, breaking this Kreimas pairing by applying circularly polarized light. So on the absorption of a circular photon, only a single body excite. So the Kreimas pairing, the spin up at K, spin down at minus K, their pairing is broken by this circular excitation. This is well demonstrated around 2014 at around that time. Our motivation is that not only circular photon, like something circular or circular something like a hurricane, the circular phonon can also provide the time reversal braking feature. So we want to provide the example of this kind of the time reversal symmetry manipulation by circular something. So before we discuss this effect of phonon, let us first review the phonon structure of this material MIS2 and this low-lying optical phonons, 4 branches of low-lying optical phonon. But the lowest optical phonon, E double prime phonon, is the most important. And so on the spin, we calculate the time evolution of spin. Please remember that we first calculated the electron spin state, and by taking the expectation value, we calculated the time evolution of spin. And we intentionally, artificially pumped a specific phonon, and the effect of a specific phonon is mostly negligible on the time evolution of a spin, but the very particular phonon, E double prime phonon, has a very significant effect on the spin dynamics. So this phonon, this phonon has the strongest effect on the spin dynamics, and on excitation of linearly polarized E double prime phonon, we plotted the time evolution of spin on this the SX SY on this below sphere, and its evolution shape shows something strange behavior, and we first calculate time evolution of a spinor state, including the spin-orbit coupling, and we calculate the spin dynamics at the below point. And after or close examination, we found that the lattice distortion along the phonon eigenvector, when the lattice is distorted by y direction, spin is deflected along the y direction. So the very phenomenological model that we can describe that the lattice distortion induced by phonon can provide a kind of the oscillating magnetic field. So we may phenomenologically depict that the effect of lattice dynamics on spin can be described by the oscillating the magnetic field. And the E double prime phonon has a double degeneracy. The linear combination of a doubly degenerate phonon can provide the circular phonon. So if the linear phonon provide the oscillating magnetic field in y direction, the circular phonon can provide a kind of some rotating magnetic field, something like this way. So here in this in this description of the effect of circularly rotating phonon or the rotating magnetic field by this by this description, I would say that in this phenomena we have two kind of rotating mechanism. One is that the Lamarck rotation. Lamarck rotation is that when there is a static magnetic field, the spin should precede by this the torque term of the magnetic field on the spin. And also in this case, the magnetic field itself is rotating. So these two combination of rotation between the phonon rotation and the Lamarck rotation, the spin has a very complicated flow shape rotation, and the the spin-orbit coupling term linearly depend on momentum. So the spin at the k valley and the spin at the k prime valley has opposite sign on the spin-orbit coupling. So in this combination of two rotation, the electron spin near the k valley and the electron spin near the k prime valley has some kind of the opposite effect. So then the spin rotation, this k valley and the k prime valley has different responses to this one-way circularly rotating phonon. So in summary, we can say that the exact opposite nature of the k spin up at k valley and the spin down at minus k valley, the Krimas constraint now released, and further we calculated in time average sense, the circular phonon produce the net spin value. So we gave a name that this is kind of the valley magnetism. Magnetism here means that the net spin value. So this is an example how the circularly polarized phonon breaks the Krimas pairing or the time reversal symmetry of the solid state. So the summary, the absorption of a circular phonon breaks the Krimas pairing. The excitation of the low frequency phonon, low frequency excitation and the pumping of a circular phonon can also provide the example of time reversal symmetry breaking. So let me summarize this talk. So basically we are interested in the description of the light matter interaction in the framework of quantum theory by performing the real-time evolution of calculation. And in this talk, I presented the two specific examples. One example, this method can calculate the intrinsic response quantity like the Hall conductivity. And we obtained the Chern number and the spin-Hall conductivity of a quantum spin-Hall system. And also another example, we showed you that the Ehrenfest dynamics of a spin-phonon calculation, and we showed that for the case of the MOS2, one-way circularly polarized, the circularly rotating phonon can contribute to the breaking of the Krimas pair. Thank you. Thank you very much.
Thank you very much, Professor Park, for a very interesting talk. Are there any questions? I could ask a quick question, mainly for clarifications. For your spin phonon dynamics, you basically prepare vibrationally excited state using some oscillating magnetic field and look at time evolution of electron dynamics. Is this way of treating vibrationally excited state using oscillating magnetic field a usual thing in the field? I don't know, so I'm just curious.
Yeah, actually, let me show you the page. Wait. Sorry, wait. Oh, yeah. Actually, what we did is that we didn't we didn't provide oscillating magnetic field. What we did is that just we just what is we yeah. We just described the phonon as a classical vibration of atom. So the atom is vibrating, atom is oscillating. This is time-dependent atom position, but actually what we did is that the classical vibration oscillating of atom and scalar potential. This is the ionic potential. You can say that the one of our potential, the center, the originating from the center. This we provide this Korn-Sham scheme, this oscillating scalar potential, because this this oscillating scalar potential also affect the spin-orbit coupling term. So this oscillating potential basically affect this spin direction, and as a result, the effect is modeled this way. But this is our the result. But what we calculate is that what we calculate is we just we didn't apply the magnetic field. We just we just calculate the electron spin in response to the atomic vibration through the SOC.
Okay, thank you very much. Are there any other questions or comments? Okay, if not, then let's thank Professor Park one more time for a great talk.
Thank you.